So yesterday during recitation, in an effort to stop some feedback from happening, I turned off my microphone, and then like a dummy, I failed to turn it back on again. So I wanted to make this video in case anybody who was trying to watch it over the internet wasn't able to hear me, or if anybody who was there just wanted to review. So this will cover questions 1 through about 3.5 on homework 2. And it shouldn't take us too long. Okay, so first thing, the homework makes reference to your textbook. This is your textbook. If you didn't already know, it's called Principles of Vibration and Sound, and those are the 2 authors there at the top if you want to procure it. I am going to copy the relevant page out of the textbook that you'll need to solve the homework problem. So even if you don't have the book, you'll be good to go at least for this week, just with the PDF that I've actually already put up with the recitation materials. Okay, so my email, please reach out if you have questions about anything. Do you know where to find the recitation resources? If you are looking at this video, you probably do. All right, so question 1, the waveform y of x comma t equals 8 sine 4t minus 5x, and it's propagating along an infinite string. Assume that all values are in standard units. Determine the amplitude, frequency in hertz, wave number, wavelength, and propagation speed of the waveform. Okay, so what it's asking us for is really just to be able to interpret this thing and know where to find this stuff. There's a little bit of calculation we need to do, but really not a whole ton actually. So we've got this, okay? Our amplitude is A, okay? Our angular wave number is K. That's like your, what do they call that? Like the frequency of position. There's a name for that, but it's like frequency as it relates to position. We've got our angular frequency, our frequency in time right there, omega. We've got a time variable. We've got our horizontal position variable, and we also have this phase term, which actually don't have in the problem. It asks for amplitude. It asks for, I think, angular frequency. Let's see. It asks for amplitude, it asks for frequency in hertz. Don't forget, you're going to be able to read angular frequency in radians per second right out of the problem statement, but you will have to convert that to frequency in hertz. And remember, omega equals 2 pi f. Let's write that in here. Omega equals 2 pi f. Wave number you can read right off of there. Wavelength, we're going to need an equation for that and propagation speed. And I made you this table and it has some equations in here. So you've got propagation speed and wavelength right there at the bottom. And those are really just plug and chug when you have this information and you're looking at this. Okay. I think that should get you through it. The second part of that question says calculate the transverse velocity of the element located at x equals 0 at time t equals 0. Well, how does velocity relate to position again? That's right. It's the first time derivative, right? So if you take the first time derivative of this bad boy right here, then you should be able to figure that out. Okay. Okay. Question 2. So this one, if the last one is plug and chug, this one is even at least as plug and chug, if not maybe more so. Consider a simple guitar with a 1 nylon string whose mass per unit length is 9.5 times 10 to the negative 4 kilograms per meter. Compute the propagation speed if the string is under 65 newtons of tension. So this string is fixed at both ends. That's how guitars work. I gave you, where is that? Gave you some information. It's kind of tucked down here. Okay. We've got equations when we're talking about strings fixed at both ends. We've got equations for propagation speed. We've got equations for angular frequency. We've got Fourier coefficient equations. We've got all sorts of fun stuff. So we wanted to know a propagation speed. There's an equation down there that should get you all set up. We've got a length here. If the string is 63 centimeters long, compute the fundamental frequency of the string. I gave you an equation for omega n, and you can convert that into f sub n, f sub 1. Okay. A perfect fifth is the musical interval corresponding to a pair of pitches whose frequencies are in the ratio 3:2. If the nut of the guitar corresponds to x equals 0, and the bridge of the guitar corresponds to x equals L equals 63 centimeters, at what position along the fretboard should a fret be placed to produce a pitch whose frequency is a perfect fifth above the fundamental? Well, we know F1, we just calculated it in the last part of the question, right? We can easily figure out what 3/2 of that value is, and then just work backwards. So this is going to be the same equation, or the same equation we used for the second part of this one, and that should get you all the way home with that one. Okay, those guys are pretty easy, and that might well be in order to make up for how tricky parts of this one are. And tricky might even be the wrong word. It's just like you saw in lecture today, it involves some really ugly integrals. Okay, so we're not gonna talk about the MATLAB part of this, just kind of the first half here. A string of length L is fixed at both ends and plucked to a height H at point X naught equals L over 4 and released from rest. Evaluate the integrals given in equations 2.17 and 2.18 of the textbook to determine a general expression for the Fourier coefficients A sub n and B sub n. So I reprinted that page in the book. There's your integral for A sub n and your integral for B sub n. And I also gave them to you right here. Before you can evaluate these integrals, you have to know what y of x comma 0 is. What does this string look like at time 0? And what we're going to do is we're going to kind of draw it out. So let's do something like this. Okay, so here's L, here is 0, right? Let's say I'm plucking this string at 3L over 4, so 3/4 of the way along it, right? Maybe there-ish, to a height H, at a height H, right? I'm gonna get something that's actually super geometric. It's just made of straight lines. I'm not very good at drawing straight lines apparently, but these are supposed to be straight. And it's actually pretty easy to figure out what the equation for y of x comma 0 is, because we know some important stuff about it. We know for this guy right here, we know the y-intercept already. It's 0, right? And we know the slope because we know what this point is, right? And we know what this point is, so we can put this in y equals mx plus b form. And we can do the same thing for this part, right? In this case, we don't know the y-intercept, we know the x-intercept, but that's almost as good. We do know the slope, or we can figure out the slope. And once we've sorted that out, we just have two lines, and it's a piecewise equation, right? This is 3L over 4 here, right? So this line, the equation for this line here is going to run from 0 to 3L over 4 in this case. And the equation for this line here is going to run from 3L over 4 to L. All right, so we've figured out what our y of x comma 0 is. And so we can go ahead and put those in here in these two equations for the Fourier coefficients. We are going to have to split those integrals apart. We're going to have to do one integral from 0 to 3L over 4, and then another integral from 3L over 4 to L. For A sub n, we want to know the first derivative of y of x comma 0. And we know that the first derivative of a position equation is going to be velocity. And we know that in the case of a plucked string, where you've just sort of like lifted the string off of the neck of the guitar or whatever, and you're holding it there ready to release it at t equals 0, we know that v of t equals 0 is 0, right? So because that's true, it's not moving, right? Because that's true, then this whole thing goes away, right? You only have to worry about this one below. That wouldn't be true if we, for example, set that string into motion with a known velocity, right? Then y of x comma 0, that would be 0, right? Because why would we be 0? It'd be sitting on like the next still or whatever, or sitting at position 0, but velocity wouldn't be 0. The initial velocity would be some value, right? So in that case, b of n would go away, but we'd be stuck with a of n, and we'd have to figure that one out. So where are we at? We've got two equations for y of x comma 0 in these at these two like sections, right? And now we've just really got to run our integrals, and we're not going to go that far here, but I'm going to tell you this. Yes, those integrals are gross. You saw that today in class. They're unwieldy and they have many terms, but they reduce to something manageable. So if you end up with 11 terms at the end, right, you've done something wrong and you need to go back, right? They do simplify into something pretty manageable. I saw that today in class too. And number two, it's easy to check your work. And what I mean by that, let's see if I put the whole problem statement in here. Yeah, it says the MATLAB, this is the third part here, the MATLAB function Fourier_coefs.m evaluates EQ equations 2.17 and 2.18 using a discrete sum to compute the Fourier components of a Pluck string. Initially set the spacing, blah, 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 blah. Check your answers to part B. You should get the same results, right? So if you're unsure whether you got where you needed to with the integral, run this MATLAB function and check them. I mean, you have to do that anyways, but hopefully those 2 points make the that super ugly integral a little bit easier to swallow. And that's as much as I wanted to go through for this recitation. Next week's recitation, we will talk about all the MATLAB stuff. I think that's it.